Hello everyone. In the last class, we explained the principles and analyzed the physical conditions of transformer no-load operation, the difference between main magnetic flux and leakage magnetic flux, the method of selecting the positive direction of physical quantities, and no-load current. Today, we will continue with the content of the previous class and discuss other physical quantities, as well as the electromotive force balance equation, no-load equivalent circuit, and phasor diagram methods. Let's first take a look at the primary side voltage U1, which is the power supply voltage of the transformer. When analyzing the working principle of the transformer, regardless of whether the transformer is unloaded or loaded, and regardless of how the load current changes, the magnitude of U1 is considered constant. Looking at the no-load loss of the transformer, the active power loss inside the transformer during no-load operation is called no-load loss, represented by Pu0. The no-load loss includes two parts. One is the copper loss generated by the no-load current in the primary winding. The other part is iron core loss, which is mainly caused by hysteresis loss and eddy current loss caused by alternating magnetic flux in the iron core. The no-load current and the resistance of the primary winding are both very small, and the copper loss is much smaller than the iron loss. So the no-load loss is approximately equal to the iron loss. Use formulas to represent as shown in the courseware. For a manufactured transformer, the iron loss is proportional to the square of the amplitude of the magnetic flux density and to the power 1.3 of the current frequency. The no-load loss accounts for about 0.2% to 1% of the rated capacity, and it decreases with the increase of transformer capacity. To reduce no-load losses, the direction of improving the design structure is to use high-quality ferromagnetic materials, such as high-quality silicon steel sheets, laser-treated silicon steel sheets, or the application of amorphous alloys. Next is the electromotive force balance equation. According to Kirchhoff's voltage law, the balance equation for the electromotive force on the primary side of a transformer is as follows. The equation for the balance of secondary electromotive force is as follows. The relationship between main magnetic flux and the power supply voltage, the leakage resistance and pressure drop I0Z1 caused by no-load current on the primary winding is very small, less than 0.2% of U1, and can be ignored. Therefore, the phasor of U1 is approximately equal to the phasor of minus E1, and the effective values are as follows. U1 approximately equal to E1 equals to 4.44 F times N1 times phi m. It can be seen that when the frequency F and the number of turns N1 of the primary winding remain constant, the main magnetic flux phi m in the iron core is proportional to the power supply voltage U1. When the power supply voltage U1 is constant, the main magnetic flux phi m remains basically unchanged. The ratio of the phase electromotive force between the primary and secondary windings of a transformer is called the transformer ratio, represented by K. That is, the transformer ratio is equal to the turns ratio of the primary and secondary windings, approximately equal to the ratio of the phase voltages of the primary and the secondary windings of the transformer. For three-phase transformers, The rated voltage is the line voltage, and conversion is required when calculating the transformation ratio. You can see the formula below for details. For YD connected transformers, K equals to U1N divided by the square root of 3 times U2N. For the transformer connected to DY, K equals to the square root of 3 times U1N divided by U2N. If K is bigger than 1, the transformer is a step-down transformer. If K is smaller than 1, the transformer is a step-up transformer. Equivalent circuit under no-load condition. Equivalent circuit. For the convenience of analysis, the excitation impedance ZM parameter is introduced to represent the relationship between E1 and I0, as shown in the formula. The voltage drop formed by I0 on ZM is equal to the induced electromotive force E1, thereby transforming complex electromagnetic induction relationships into circuit relationships. Excitation impedance ZM is an important parameter in transformer analysis, where Rm is called excitation resistance, corresponding to the equivalent resistance of core loss. Xm is called excitation reactance and the equivalent reactance caused by the main magnetic flux in the core coil, that is, the ability of a unit excitation current to generate the main magnetic flux, is affected by the saturation of the core magnetic circuit. Due to the saturation characteristic of the magnetic circuit, Zm is not a constant and decreases as the saturation degree of the magnetic circuit increases. Due to Rm being much larger than R1 and Xm being much larger than X1, sometimes the leakage impedance is ignored and the no-load equivalent circuit is only a Zm component circuit. In the case where U1 is constant, the size of I0 depends on the size of Zm. From an operational perspective, it is desirable for the I0 to be as small as possible. Therefore, transformers often use high permeability materials to increase Zm and decrease I0, thereby improving operational efficiency and power factor. The method of phasor diagram when the transformer is unloaded, according to the electromotive force equation, U1 equals to minus E1 plus 10 times R1 plus J10 times X1. When the transformer is unloaded, the phasor diagram of the transformer during unloaded operation can be drawn. The drawing steps are as follows. First, using the main magnetic flux as a reference phasor, plot the main magnetic flux phi m on the x-axis. Second, make electromotive forces E1 and E2, both of which lag by 90 degrees with respect to phi m. Third, the reactive component I mu of the no-load current I0 is in phase with phi m, and the active component IFE of the no-load current I0 leads by phi m 90 degrees, resulting in a synthesized phasor I0. Fourth, take the phasors minus E1, I0, R1, and Ji0x1 in sequence and add them together to obtain the phasor U1. The phase angle phi 0 between U and I is the power factor angle of the transformer when it is unloaded. Generally, the active component is much smaller than the reactive component, so A approximately equals to 0. Phi 0 approximately equals to 90 degrees. And the power factor cosine phi is very low during no-load operation. In order to clearly see the phasor diagram, I0R1 and GI0X1 in the phasor diagram has been intentionally enlarged. Now let's summarize the content of no-load operation. First, the primary side electromotive force and leakage resistance pressure drop are always balanced with the applied voltage. If the leakage resistance pressure drop is ignored, the magnitude of the primary side electromotive force is determined by the applied voltage. E approximately equals to U1. Second, the magnitude of the main magnetic flux is determined by the power supply voltage, power supply frequency, and the number of turns of the primary coil, and is basically independent of the material and geometric dimensions used in the magnetic circuit. U1 approximately equals to 4.44 times F times N1 phi. Third, the magnitude of no-load current is related to the main magnetic flux. The number of coil turns and the magnetic resistance of the magnetic circuit, the better the magnetic conductivity of the material used for the iron core, the smaller the no-load current. Fourth, reactance is the ratio of the electromotive force induced by alternating magnetic flux to the current producing that flux. In a linear magnetic circuit, reactance is a constant, while in a nonlinear circuit, the magnitude of reactance decreases with the saturation of the magnetic circuit. That's all for today. In the next class, we will talk about the load operation of transformers. That's all for today's class. The class ends here. Thank you for watching.